Hello, the next topic is biochemists use formal potential. You see, your textbook, the quantitative chemical analysis is quite, the biochemistry oriented. So, as we have seen, the many topics are related to biochemical reactions. Okay, so this textbook is very, is adequate for the students who wants study biochemistry or biology. Okay, yeah, there are other important analytical chemistry textbooks. Okay, but most of them, uh, the uh, the text the texts are oriented to the pure chemical reactions. Okay, but here you may find that many examples biochemistry are related. Yeah, that's good for you. Okay, because I think most of you or many of you want to study biochemistry or bio-related subject. Okay, in graduate schools. Okay. Anyway, so many biochemical reactions involve protons, okay, and the pH usually is 7, yeah, the neutral pH, okay. So it is important to redefine the standard reduction potential at pH 7. Yeah, that's the formal potential, okay. Here, the most important reaction in living organisms is respiration. Yeah, this is just one example, right? Respiration involves the carbohydrate and its oxidation, the oxidation by oxygen, yeah, to yield the energy or metabolic intermediates. Okay, in the process, the protons are involved in the reaction. Okay, uh, but here's our what the problems, okay? But not the problem, but our difficult things, because if we use standard reduction potential, that assumes that hydrogen proton activity equals 1. In other words, the pH is 0. Yeah. So in order to calculate a pH 7, you have to recalculate all the reactions. Okay, that's quite much a nuisance. Okay? So it is important to redefine the standard reduction potential at pH 7. Okay? And whenever a proton appears in redox reaction, yeah, that's a very usual case. So most reactions take place in aqueous solution, right? And also, most of them involve the protons. Okay, so that means pH, yeah, pH solution pH affects the reactions. Okay, reaction rate or reaction types. Okay, and or whenever reactants or products are acids or bases. Okay, reduction potential are pH dependent. Yeah, that's very important. If the electrochemical reactions involve protons, that means that the reaction potentials are pH dependent. Okay, because pH inside the plant or animal cell is about 7. Yeah, that's very important. About 7 in neutral condition. Uh, reduction potential at pH 0 not appropriate. Okay, well, not appropriate, that means that it is simply difficult to consider the reduction potential at pH 7, right? So it is convenient to redefine the standard reduction potential at pH 7. Okay. Yeah, of course, if the reactions don't involve protons, okay, the, the reduction potential doesn't uh, is not affected by pH. Okay, so in that case, the electrode reduction potential is pH independent. Okay, here's an example. At pH 0, vitamin C is more powerful reducing agent than succinic acid. Okay, that's the fact. However, at pH 7, this order reversed. As you know, vitamin C is a mild reducing agent, yeah, at pH 7, but at pH 0, in a very acidic condition, its reducing power is more than that of succinic acid. Okay, the standard potential is defined all activities in a cell reaction unity. Okay, all the activities are unity. So, but as I said, uh, when protons are involved, that means the pH is 0. Okay, so that's not realistic. Yeah? So we have to recalculate the standard reduction potential, yeah, at pH 7. That's called the formal potential. Okay, actually, formal potential is a reduction potential that applies under a specified set of conditions. Okay, not actually. It doesn't need to be a pH 7, but since we are now dealing with the biological reactions. In that case, pH 7 is the most common pH. Okay? All right. So here we write the formal potential E0 prime here. E0 prime. It reads E0 prime. That's the formal potential at pH 7. Okay. This is the most common case. All right. Yeah, this table lists the reduction potentials of biological interest, yeah, the standard reduction potential, as well as formal potentials at pH 7. For example, oxygen reduction, yeah, in acidic condition is the E0 is 1.229 volt. So oxygen is a very powerful oxidizing agent. Okay, but since this reaction involves protons, okay, so it's E0 uh, at different pH that standard reduction potential changes. Okay, at pH 7, E0 value changes from 1.229 volt to 0.81 volt. Okay, you'll see how to calculate this new value. Okay, but here ferric ion is reduced to ferrous ion, but it doesn't involve protons. Okay, so its standard reduction potential at pH 0, 0.771 volt is still the same at pH 7, right? Because there is no proton ions here. Okay, likewise, this iodine reduction to iodide is formal potential and standard reduction potentials are the same. Okay, but yeah, likewise, the cytochrome A also, yeah, it gives the same potential, yeah, regardless of solution pH. But this oxygen reduction too, what hydrogen peroxide, it involves two protons and also two electrons. Okay, there is the number of protons and electrons are the same. In that case, E 0 prime is different. Okay, and like that, yeah, you see, you take a look. Okay, so if the reduction potential depends on pH, and if pH increases, in other words, if the solution becomes more and more basic, then the standard reduction potential also decreases. Okay, you see this one it decreases, yeah, quite a bit. Yeah, all decreases at pH 7, except or in these cases where the protons are not there. Okay, Okay, so everything is straightforward, yeah, not very difficult. Yeah, here, yeah, this slide shows how to calculate E0 prime at pH 7, okay, at different pH. Okay, let's just consider this general case. Now, A plus Ne equals B plus H plus, okay? Yeah, A and B can be acid or base, or they don't need to be acid or base, okay? Anyway, this one says this reaction, this electrohep reaction, involves a proton here, right? And then let's calculate the formal potential. This one, we write the Nernst equation for this one, and E equals E0. This is the standard reduction potential, and since we are using this one, that's this common logarithm, and we assume that the reaction temperature is room temperature, which is 25 degrees C, and then this part is all the time is a constant, okay? 0.05916 divided by n, okay, and logarithm term here, all right. But let me see, this log term can be converted into this one, okay, right? And this one can be rewritten equals, we expand this part, yeah, and here we want to make the final equation like this one, yeah? Logarithm of this one, formal concentration ratios, okay, instead of this equilibrium concentration, okay, yeah, to make this one, yeah, and then there will be several other terms in this equation. So at page 7, this one, this term, including um, standard reduction potential and other terms, it is defined as formal potential, okay, yeah. So best one is to take an example, yeah, to understand this equation, okay. Okay, now let's consider the acidic system that takes that undergoes electrochemical reaction, okay. For example, this HA, here HA is what, weak acid, yeah. The equilibrium concentration of HA form equals alpha HA multiplied by F, and it is given by this simple equation, and A minus the concentration. In the meantime, it is alpha A minus F, okay. It takes this form, yeah? Here the formal concentration is the sum of equilibrium concentrations of HA and A minus, okay. Yeah, this is from the mass balance. And therefore the diprotic system, yeah, this one is a little bit more complicated, but still, H2A, H2A, the equilibrium concentration is given by, yeah, you can write very systematically, okay, these equations, okay. And the formal concentration is the sum of all these three equilibrium concentrations, okay, yeah. That's our basic equations. And as an example, let's take the ascorbic acid, that's vitamin C, yeah. This is this white crystal is in a reduced reduced state, and it undergoes oxidation, okay, and it becomes this one, dihydroascorbic acid. Yeah, this is oxidized form, and ascorbic acid, whose another name is uh, the vitamin C. Yeah, this is actually a reduced form, okay, and it undergoes two protons and two electrons, and to become this one, all right, and E0 value is 0.390 volts. But now question is, what is the formal potential? What is the the reduction potential at pH 7. This one, this first thing we have to do is to write the Nernst equation. Okay? So this one can be rewritten, very in this simple form. Okay, T plus 2H plus 2E minus equals H2A plus H2O. Here, important is that this one, this oxidized form of ascorbic acid, but this is not a acid or nor base. Okay, but this one ascorbic acid, there are two dissociable protons in the structure. This one, they are acidic protons. Okay, so ascorbic acid is a weak acid. We need ascorbic acid at least 1 gram per day. So, but if you take this ascorbic vitamin C pill, and then you immediately your tongue feel the very sour taste. Okay, because the protons here, two protons can be dissociated. All right, so ascorbic acid is acid. Okay, it's a weak acid. Whose pK1 is 4.10 and pK2 equals 11.79, and we can write this one H2A, right? H2 is important because it contains two dissociable protons here. Okay, and so for this equation, we can write this Nernst equation here. Okay, and we simply we can very easily write this one. E equals E0 minus 59.16 millivolt divided by 2 multiplied by logarithm of this one. Okay, here, and D here, D, this form is neither acid nor base, so we can simply say the this equilibrium concentration equals this formal concentration. Okay, that's very simple. And here, to calculate H2A form, we use here this equation. Okay, here H2A form, this concentration is given by this equation. Okay, and then we substitute these two into this Nernst equation here, right? Although it is looking rather complicated, but now we extract this part. Okay, the logarithm of the formal concentration ratio. Okay, here's 1 and here's 2, and then all other forms are now taken out of this, taken differently. Okay, should be taken independently, and then we rearrange this equation. We can write this part. E equals E0 minus this constant, multiplied by log of 1 over this one, and minus this one multiplied by logarithm log of formal concentration ratios. Okay, and now this part is called the formal concentration at any pH, but now we consider only pH 7, and then we know already K1 and K2 values, and also at pH 7 the proton concentration equals what? 10 to minus 7 molar. Okay, and then after all we get this formal potential is 0.062 volt. Okay, because this one E0 value for ascorbic acid is already known. Okay, let me see where. Here is the ascorbic acid. Let me see, let's find here dihydroascorbate plus 2H plus 2E minus is ascorbate, and H2O. This one E0 value is 0. Plus 0.3 0.90, and at pH 7 it is 0.058 volt. Okay, 58 volt. I don't know why it is a little bit different. Okay, anyway, yeah, it's almost identical. And this one, now you can plot this formal potential versus pH. Okay, you change the pH. In other words, you change proton concentration and you plot the formal potential change. And then uh, you will get this solid blue line. Yeah, it uh, decreases as pH increases. Okay, linearly decreases, and then at this point, yeah, it also linearly decreases, but the slope changes. And another point here, it also not doesn't decrease anymore. It flattened. Okay, here. So when the pH is less than pK1, okay, in this region, and slope is what, 59.16 millivolt per pH here. Okay, and at this region between pK1 and pK2, okay, the slope is just half of this one, first one. Okay, and then beyond pK2, slope is a 0. Okay, to confirm, yeah, this one, yeah, you can calculate, this one using Excel. With Excel, you can easily, uh, you see, you can construct this figure. Okay? When pH is smaller than pK1 here, let me see, K2 is so small, maybe you can ignore this part. Okay, and also K1 compared to proton concentration is very small, so this term also removed. Yeah, so the formal potential dependence on pH, yeah, actually this is squared, and this two is cancelled out each other. Okay, so the formal potential dependence on pH is about 69 millivolt per pH. But in this region, okay, this part, the first term and second, the last term may be ignored. Here, only proton concentration here. Okay, and then since it is already 2 is here, the slope is just a half of the 59 millivolt. But beyond uh, the pK2, and the first and second terms are ignored, and so the formal potential doesn't depend on the pH. Okay, and actually, let's the real experiment, it shows this one, this what the dotted line. Okay, yeah, you can identify the region 3, this region and this region and this region. Okay, yeah, so your observation, experimental observation, agrees with this theoretical expectation. Okay, yeah. Okay, yeah, this is the end of chapter 13. Okay, chapter 13 deals with the fundamentals of electrochemistry. Okay, and that this chapter is very important, and it laid the foundation for the subsequent chapters for electrochemistry. So I really encourage you and urge you to study very carefully the chapter 13, and then with the full knowledge of chapter 13 you can move on to the next chapter. Anyway, I selected these problems, then you try to solve those problems. Okay, and as I mentioned in the notice, in the announcement, that the solutions are available from the internet. Okay, you visit internet, website, then you can find the solutions. So in the first, try to solve by yourselves, okay? And if you cannot, then you can report to the the solutions, okay? Okay, now let's stop.